it is fabricated, which provides the advantage like what yesterday we talked. And we also talked about how it works. As I told you, it is similar to MOSFET. We know that MOSFET is a voltage control device. MOSFET is a voltage control device. That means we are supplying voltage at the gate of the MOSFET. So the current flowing from the drain to source, it will be controlled. So if I vary the VGS, which is nothing a gate voltage, the IDS, that is drain to source, current is varied. Okay, so the output is current, which is controlled by input voltage, which is opposite to what we are talking about transistor. So this has advantages, correct? But that means the input is no current is taken. So the MOSFET doesn't consume power from the sensor or any other previous device from where it is getting input signal, but it is able to deliver required current to the load, which is connected to the MOSFET. So that's what the advantage. It is a voltage control device. So there is the advantage of MOSFET, correct? So MOSFET is used as input stage in the IGBT. So same advantage is available in the IGBT also. And by controlling input voltage, gate voltage, we are able to control current flowing from collector to emitter. Please note that collector to emitter. In case of MOSFET, drain to source current, correct? Drain to source current is controlled in case of MOSFET while controlling the gate voltage. But in case of IGBT, you control the gate voltage, correct? You control the gate voltage because the gate of the MOSFET forms as input for the IGBT. Already we saw the symbol. So when I change the gate voltage, the collector to emitter current is controlled. Output stage is a transistor. Already I told transistor advantage of low saturation voltage across VCE. So power dissipated across the transistor part of the IGBT will be minimal compared to MOSFET. And apart from that, the transistor can handle a high current with low losses because VCE is very low, 0.2 volts. But in case of MOSFET, I told you yesterday, still very high. So because we also, these points already noted, we know that the application also said. So I think I stopped here. Basically, this is the internal schematic of IGBT. Take the pictures. Very important. Exam, it is expected you have to draw this picture with properly. So you can know that. So this is the cut section view. Think like that. The cut section view of IGBT. It is a 4-layer device. I told you it is a 4-layer device. The first bottommost. This is the bottommost layer, which is called P plus. P means P-type material, plus means highly doped. Whenever you see plus symbol along with P or N plus, you can say that the plus symbol represents highly doped. Highly doped. We know that I talked about when you talk mechatronics, semiconductor physics, I talked about a transistor. You take a pure silicon, which is an insulator, you add the impurities like pentavalent element like a phosphorus. So it becomes a P-type material. And if you add aluminum, trivalent element aluminum, it becomes a P-type material where the holes are majority carrier. And in case of this one, electrons are majority carrier. So the insulator, pure silicon, is converted to N-type material by adding impurity, or which is called a doping. It is called a doping. That means the process is from this one. So if I add more aluminum, correct? Al is a trivalent element. Aluminum is a trivalent element. That means its outermost orbit of individual aluminum atom has 3 electrons. Outermost orbit is called a conducting this one. There you have 3 electrons. Then if I have phosphorus P, it has penta. Penta means 5 in Greek, correct? So 5 electrons are there in outermost orbit. So it will become a N-type material. If I add this one, phosphorus, this will become a N-type material. Already we know this will become P-type material. Okay. Now, if the amount of the number of atom, for example, generally I take a cube of silicon, correct, in which I have, for example, 1000 atoms are there. Si atoms are 1000. That is pure insulator, non-conductive. This is a non-conductive. Now I add, for example, say some 50 aluminum atoms. Correct? I add, what will happen is this will become a p-type material, which is insulated this one. I'll say that this p-type is lightly doped. Correct? You have 1000 atoms. 1000 atoms originally, out of that 50 atoms were replaced by aluminum atom. That means in p-type material, I have 950 silicon atoms and 50 aluminum atoms. In the same, because same volume cannot add more in this one. The volume is fixed, correct? In a volume, original volume, for example, 1 cubic mm. For understanding purpose, we know that Avogadro number, if you see the number of atoms, will be very big number, 10 power 23, 24 for a cubic, this one, mole, 1 mole of matter, correct? So, trillions of atoms are there, very, very small. Understand why 1000 atoms are in one of this one. In which I added aluminum, that means 50 silicon atoms are thrown out. I added aluminum. 50 atoms. So that means this is become p-type material. Instead of that, if I add, for example, 200 atoms or 250 atoms, aluminum atoms, then what will happen? 750 will be silicon atoms. For example, 250 will be aluminum. So this is called as highly doped p-type material. Highly doped p-type material. P-type semiconductor. What is the advantage? As I add more number of aluminum, in case of p-type material, or phosphorus atom in case of n-type material, more number of charge carrier, whether in case of p-type material holes are called positively charged, which is called conducting elements. In case of n-type material, electrons will be added. As I add more number of phosphorus atom, more number of atoms, so conductivity increases. The p-type material conductivity or n-type material conductivity is directly proportional to doped amount of impurities. Please note that pure silicon, nothing else is there. Pure silicon means there's no other impurities, no other elements. If I see 1 cubic mm, I said 1000 silicon atoms. I don't see any other element in periodic table except this one. So it is a pure insulator. Now I want to make that insulator as a conducting material by adding conducting elements like aluminum or phosphorus. Phosphorus is electrical conducting element. Aluminum also electrical conducting. Only thing is pentavalent, trivalent. By doing that, I can create n-type or p-type. That is what is semiconductor physics is there. So already we saw about this when we talking about diode, triode, the transistors, and also SCR, all those things. Similar to that, in IGBT, it has 4 layers. This is the layer 1, first layer, p-type, p plus, highly doped. Next layer is n minus, that is n-type, that is second layer. Second layer is a n minus, that is n-type material, highly doped. Minus symbol says it is n-type, that means more number of the phosphorus added. The third region is again P. I don't put plus or minus. I say that it is lightly doped. Correct? We say that no symbol is that. This is lightly doped p-type material. It is the third layer. Correct? The last layer is N plus. This is heavily doped. I can say that heavily doped N-type material. That means more electrons are there compared to this. This is lightly doped. This is heavily doped. So what it means? N minus means you can say that very, very less number of this one. Phosphorus atom or other. For example, out of 1000 silicon atom given volume, you added only 10 phosphorus atoms or 20. So that means the conductivity is there. It is not insulator. It has become an N-type material because you added the phosphorus. But number of electrons is very less. Out of 1000, only 80 silicon atoms are removed. Instead of that, we added 20 phosphorus. That means 20 electrons only available. So I can say that it is lightly doped. So that means its conductivity will be less. Yeah, N plus maybe instead of 50 or 20 phosphorus atom, you would have added 200 phosphorus atom. That means 800 will be silicon, 200 will be pass plus. That means 200 additional electrons are available. So the conductivity is very high. Okay. So the conductivity is very high. Okay. Don't worry, because somebody is calling. I am not going to pick the phone because I'll be later we'll talk. Okay. So there are 4 layers. This one. So between each layer, between 2 layers, a junction is formed. Correct. We know that PN junction. PN diode means I have P type material, N type material. Both are. This is called a junction. Correct. As a J1. Similarly, transistor, you have P, N, P. This is junction 1. This is junction. If two type of P and N are touching each other, it forms a junction. So this has 3 junction. I say this is J1 junction. So this one, and between these two is called J2 junction, and the third junction is between P and N plus. So this is J3 junction. So I can say that my IGBT is a 4 layer. It is a 4 layer, 3 junctions. Correct? There are 3 junctions are there. Alternate junction P plus, N minus, P and N plus. So each now from this I'll be taking connections. I told you IGBT is a 3-terminal device. What are the terminal? One terminal is called as this is the collector terminal. You can see that the black color is nothing a metal contact. Black color wherever you see, that is like a metal contact. That is a metal contact. We can see that this is between P, that is called a collector of the transistor. I told you inside the IGBT you have 2 devices. One is a transistor, other one is a MOSFET. The transistor has 2 terminals. One is called collector, other one is called emitter. That's what we are taking. Collector terminal is taken out from the P plus terminal. Okay, P plus terminal. Then emitter is taken from N plus. You can see that this is emitter. This is the metal contact, black color metal contact, which is touching the N plus. Okay. So then the third contact is called as the gate. In case of MOSFET, the gate is not touching any of the semiconductor. You can see that in between, this is the metal contact, black color is the metal, correct? Gate contact, which is deposited over a insulator. Correct. So below that, you have the N plus, all the semiconductor materials are there. But please see that the metal contact is not touching the semiconductor, and it is insulated, separated by silicon dioxide. SiO2 is an insulator. Silicon is an insulator. SiO2 also an insulator. That is deposited. This forms the gate. In case of MOSFET, you have similar to MOSFET. I think I thought I just showed in the previous class when I talked, but anyhow, for the completeness, I will take after the IGBT. Okay, so that means the 3-terminal gate, which is a part of the MOSFET, which is the input through which I am applying input. Please see that this is input voltage. VGE, voltage applied to gate terminal from this power supply with respect to emitter. Correct? With respect to emitter, this power supply, this is called control input. This is called as a control input. Okay. And VCE is the connected between emitter of the transistor and the collector. Okay. That's what. So now that you understood what there are 4 layers, and this equivalent circuit is shown here. I have a transistor which has a emitter, collector, and base. This is my base. And the base of the transistor is connected to the drain of the MOSFET. Okay, when we talk about this, I can say that I can divide into 2 parts. This is my input stage. This is my output stage. Output stage consists of transistor as a base, emitter, collector, and I'll be connecting my load like this. This is my load resistance RL or RC connected between the collector and the emitter through the power supply. What is this power supply? For transistor, we say VCC. Okay. So where is my input given? My input signal is given here. This can be a sensor or any other input from other device like a microcontroller, DA controller, something control input. This can be called as other control input. Will be supplied as voltage. Please note that here what we are supplying is VGS. This voltage called VGE. Please see the why I am calling EG. In case of MOSFET, voltage between gate and source. But here, voltage between gate of the MOSFET and emitter of the output stage of the IGBT, which is a transistor. So we say VGE. So this is the input control. If I vary this VGE, if VGE is varied from 0 to 5 volts, just like MOSFET, what will be the output voltage? This IC. IC is the output flowing from power supply to the emitter comes to collector. So the current is flowing like this. So this is my load, correct? This can be a motor or a solenoid, whatever it may be. This voltage, generally I told you that very high voltage. It can be 4,000 to even 6,000 volts. Yesterday I told you. IGBT works even 400. It need not be always 400. It can be 100 volts also. But we say that maximum voltage can go to 400 to 6,000 volts also. Supply voltage connected to collector emitter terminal of the IGBT through which load. So that means if I vary my VG, which is input 0 to 5 volts, my ICE or IC, correct? This is called collector current because the current is flowing collector to emitter, correct? So power supply, like some book they put ICE, some book just put IC. Already we know that IC is varied from 0 to maybe 100 amps or 0 to 500 amps, depending upon the voltage, all those things, correct? So that is why the IGBT is called as voltage controlled semiconductor device for high voltage application. Let me clear this. You can take the picture, note down, correct? So here I am giving the input voltage. I will make it. This is my VGE, varied from 0 to 5 volts. Here I connect my load RL, and this is the supply voltage given to this one, plus minus VCC, and this is my IC. IC is the output, VG is the input. Right? If I vary this, the IC will vary from this one. So the power supply to load will vary. This is how IGBT works. You understood? Okay, fine. Next thing what I want to show is, this is a simplified, please note that this is a simplified diagram, simplified IGBT internal circuit. I can say internal circuit. I got one more because you can find different books, internet, all those things. The other one was this one. I got it from this Toshiba. They are also making IGBTs. Please notice, Toshiba is a semiconductor. They are semiconductor. Toshiba makes chips, many TV, correct, computer. Also, they do a semiconductor division where they are manufacturing IGBTs. Also, they are selling. From the website, I got it. This is a detailed. I can say that detailed IGBT internal circuit. Okay, they call detailed IGBT input circuit. Please see that absolutely there's no difference. You have a transistor. Here also you have a transistor. This is the output stage final. Across this only we are going to connect our load and RL and connected to this VCC plus minus. This may be 400, 600 or 1000 depending upon the load voltage. For example, it can be a motor, correct? High voltage motor which works after the kilowatts. 50 kilowatt, 100 kilowatt. So it may consume 1000 volts, 2000 volts. Okay. Then that is my input and control signal. Same thing what I told. This is my VGE, varied from 0 to 5 volts. But only thing is, they are showing internal load resistance for the MOSFET. Correct? MOSFET also you need to control the ID. What is ID? ID is called a drain current. Similar to collector current in a transistor, in case of MOSFET or FET, this is called a drain current. Drain current needs to be controlled. For that, they have internal resistance. Please note everything is a single unit. You don't have nothing except this alone you are giving. The load resistance and power supply and VGE. input control voltage. All of the whole thing is inside my IGBT of the Toshiba make, correct? So it has additional transistors and it has resistors. Again, there's a we called as a emitter resistance between these two, correct? So this is also more information about what actually this is actual circuit of the Toshiba. This is approximate. Basically, what I'm saying, output is a transistor, input is a MOSFET. This gives, and also they say how much this one, how it control current gain. Please note that already we have talked about beta, correct? What is beta? IC divided by IB is called as beta or current gain of the common emitter CE amplifier. Common emitter amplifier. Here you can see that they put alpha, correct? Alpha is also called as current gain. Alpha also called as a current gain, but it is not IC by IB, it is IC divided by IE, correct? So this is called as common, correct? This is called, so input, the current is flowing here, coming out, the control input is given on the base. This is called a common base transistor. Don't worry about it. Common base transistor, and the output gain, transistor gain is computed IC divided by IE, where IC is collector current, IE is called emitter current. Generally, IE will be very close to IB, correct? Provided beta is very high. Beta current gain is very high, correct? We know that if you remember correctly, IE equal to IB plus IC. This we saw last semester. Again, I will draw for you to understand quickly. I give voltage to my VC. This is my plus minus VCC. I am giving here VB. I have a resistor here. I have a resistor here. This is called RB. This I call as RC. This is my emitter, collector, base, NPN transistor. We know that this current is called as IB. This current is called as IC. We know that transistor is not an energy storing device. Whatever goes in, what are they going inside? See the arrow direction. I to the collector, it comes out through the emitter, because transistor cannot store energy. It is not a capacitor. It is not a inductor. So it is just a partially conducting transistor. That means it is a resistor. The equivalent circuit of transistor resistor. I told you the dynamic resistors. That means if current goes enter, it cannot be stored inside. It has to come out. So IC is going in. Here, in the base side, I am following IB also moving inside. Correct? We know that IB also is moving inside. This is IB. This is my IC. So the finally IE is coming. So that means two current are entering. One current is coming out, emitter terminal. So being a non-storage element, all the current enter should be come out. So that means IC plus IB equal to IE. This is the basic principle of transistors. And that's what we are talked about. So then if the beta is very high, correct, is very, very, very high, what will happen? We know that IC equal to beta times IB. For example, I say my beta equal to 1000. Okay. My IB equal to 1 milliamps. What my IC? IC equal to 1000 milliamps. Because multiplied by this is 1 milliamps. Okay. Now, what is my IE? IE equal to 1000 plus 1, which is IB is 1 milliamps. IC is 1000. Can I say IE equal approximately equal to 1000? Because this 1 milliamps can be neglected. Correct? Compared to 1000, 1 million is neglected. So we can say that IE equal to IC. Correct? That's what we are saying. While designing this IGBT, the gain of this beta of the transistor is doped such that beta is decided by the doping of the N and P type material. If we heavily dope, the gain will be very high. Automatically, IE will be close to IC. Then alpha will be equal to 0. Correct? IC equal to IE. So alpha equal to IC divided by IE. So both are equal, automatically becomes 0. Correct? So that means whatever the current enters will just come here. You need not write. I am not going to ask you to draw this circuit, explain. For the purpose of this one, I expect this and this. Okay. So basically, we are saying that if I vary this voltage, this current IC will vary. This IC will vary. Correct. So we have to give a positive voltage varying from 0 to 5 volts. So current will be through layer resistor going to come. That this is how it works. You understood? Okay. Now we know that the IGBT basically as a 4-layer device. Just now I told you P plus N minus. Correct. Sometimes some book just put N alone. They will put just N. If they put N alone or N minus, that means it is lightly doped. N plus means heavily doped. P plus means heavily doped. P just P or P minus means lightly doped. Just P or P minus, that means the number of current carrying conductors are less. Correct. In case of P type, it is holes. In case of N type material, it is electrons. Compared to this P plus, in the P, it is less, or P minus also less. Compared to N plus, N or N plus, just N minus will be less. That's what you need to understand. Okay. So because of that, the amount of current flowing through the device will be controlled by the doping density. That's what decides the current carrying capacity of any IGBT or transistor, MOSFET, diode depends upon the doping density. Correct? Higher the doping density, we will say that it is high current carrying capacity. It will become a power MOSFET, power transistor, power diode, power IGBT. Correct? If N plus P plus are highly doped, how much it should be doped decided by the manufacturer. Accordingly, the current carrying capacity 0 to 1 amp, 0 to 10 amp, 0 to 100 amps. Higher the amps rating means the doping density will be very high. P plus, N plus, all those things. This was just understanding purpose. If somebody asking you in the interview, since you are doing this. So it has a 4-layer. Again, I am repeating same picture here. The lowermost layer, which is called a base layer, which is also called injection layer. Note down the name. In IGBT, the base layer or P plus is connected to collect that. This layer is called as collector of the IGBT. Okay. Then you have N plus. The next layer is N minus, or which is also called drift layer. Correct. It is called a drift layer through which the please note that here you have positive charges. P itself is positive. P plus means more aluminum atoms are there because of the more holes, positive charges are there. So P plus is highly doped P layer, which is called an injection layer. Okay, we will see what is the purpose of that. Then next layer, immediate, this is the bottommost, layer 1. Layer 2 is N minus, which is called a drift layer. That means N layer, consider N-type material, you have less sparsely populated electrons. Electrons are there, but number of pass per matter doped is very less. Because of that, that's why N minus, which is called a lightly doped. Some books, they put just N. Correct? Instead of using N plus means more. Correct? N or N minus lightly doped. So, which is called a drift region. You can see that one more thing also, if you see the thickness, this is called as thickness of the layer. The N plus layer thickness is very high. Thickness is this. For P plus, thickness is this. Correct? For P, this is the thickness. For N plus, this is thickness. You can see that big layer thickness is N drift layer. Correct? This drift layer decides what is the voltage rating of the IGBT. Voltage rating. I told you IGBT is available from 400 to 6000 volt. We are talking about max voltage. Correct? We are talking about maximum voltage you can apply VCC max. Nothing but correct. This is the collector. This is the emitter. Between this, what is maximum? That is decided by the thickness of the N drift layer. Okay. Note the information. Somebody can, if you are electronics with BTech, MTech, still you are working in automobile company, somebody may ask you. That's why I'm just explaining for everybody for understanding purpose. I said so. Why the holes which are here is going to pushed. I am going to supply, what supply I am going to give? Yeah, positive voltage to the collector. This is VCC. I said this is 400 volts. There's a switch. This is my battery. Correct? I close the switch. Immediately what happens? Here you will get positive charge from the battery. Correct? So this is positive charge from battery. Inside your injection, which is P plus, already you have positive charge. What happened? If positive charges come near this one, another positive, they repel. Correct? So this positive charge coming from my battery, positive terminal, will push already in the holes into the drift layer. Correct? These holes will be pushed like this. Next figure I'll show you. These holes will be pushed towards what? Okay. Please note that here you have holes, positive charge. Here you have electrons, negative charge. But in between, you have one P layer, another low density N layer. Correct? These two layers prevents the holes. Please note that holes, these holes are attracted by this fellow. Correct? Negative charge attracted positive charge. But so the both are the dead end. This is the last layer, fourth layer. This is the third layer. This is the second layer. First layer this. And now, if I don't give the external voltage between collector and emitter, these holes which are here, they wanted to go here, but these two layers are preventing. N drift layer and the P body layer. They call it, these are naming. Please note that this layer is called P body layer. This is called a drift layer. This is called as injection layer. Correct? Injection layer only consists of the positive holes. Okay? Already they are there. Here you have less number of electrons. Here you have more number of electrons, highly doped, negative. Here you have less number of holes. Less number means I am talking compared to P plus, P region has less number of holes, positive charge. Compared to N plus region, the N drift region has less number of electrons. So that's why the symbolic. This is how it is constructed. So we know that P substrate is called collector region. Okay, it is the main base of IGBT. Correct? And during working condition, if I supply the voltage like this, correct, positive voltage and negative, this positive charge will push this holes towards this drift region. Correct? And so it push, it enters here, and finally it attracted by this, the holes are flowing. Correct? So we know that this is a PNP transistor. Output stage, what I shown is PNP transistor. Please note that again, I told you yesterday you have two type of IGBT. One is called N-channel IGBT, other is called P-channel IGBT. Now what we are talking is this is a N-channel IGBT. Okay. If you understand one, automatically you understand other things also. I'm not going to explain both, we don't have time. Okay. So this is called as N-channel IGBT. Why I am going to, you will understand within few minutes. So now if I connect a positive voltage like this, which is called a bias voltage, plus minus, this is VCC, this positive voltage will push these holes into the drift region and it will go like this and end up here. So this is the flow of holes or charge particle or current. In this case of the N-channel insulation, current is produced by flow of the holes, which is from the injection layer, P plus layer, when I apply external voltage. Without this voltage, the holes from here cannot cross this N drift layer and also P body. So that means now that's why it is going to inject holes. Okay. Now, if during working means when I apply positive voltage between this one, the holes are injected into drift region and they go toward this one and reaches finally. So the current flows between the collector to emitter. Current will flow like this. So now if I connect my load resistor RL, so it can be a motor, solenoid, it is going to be driven by this MOSFET. Next is called the drift region. This is lightly doped region. Note down, please take the notes. Correct? This is called a lightly doped region because number of electrons are less. Okay. If you have more number of electrons, the holes cannot reach. Correct. When the hole enter here, what will happen is this is a positive charge and already have an electron. These two will combine. When a hole meets a electron, they combine, they will become neutralized. That means there's no current flow. Now, for example, if I want current to flow from the collector to emitter through the load resistor, then only my device will work. Correct? So collector current should flow from here to here like this. Correct? Now, current is due to holes. Now, if I, for example, because of holes, for example, 3 holes are entering here and I have 1 electron here. What will happen? One of the hole will combine with this, it will be neutralized. It cannot reach here. So what will happen? Remaining 2 holes will go and will cross this boundary because this positive voltage is very high. Correct? Plus minus, we are giving say 400 volts or 100 volts or 50 volt positive. Once it comes here, it will be penetrate to the P, it will collect additional electron, these holes, which is the P region, and they will join here and current flow will happen. Okay. So if N plus the drift region is highly doped, for example, this is a N plus, that means the holes coming enter will all this will be recombined here, current flow will not happen. That is why they have lightly doped N region, which is called a drift region, and injection will happen here happens. Okay. So determine the voltage blocking. Another thing is the drift region thickness decides what is the voltage, maximum voltage you can apply across collector and emitter, nothing but your load resistance, motor. Correct? If I want to connect a motor, correct, this is my motor, which is 400 volts motor, means the thickness should be bigger. Correct? So this thickness, for example, 400 micrometer. I'm talking or 400 micrometer. If I want to give 1000 volts and it has to operate, means you say blocking voltage, this thickness will be 1000 micrometer, bigger thickness. Correct? That's what we are talking here. Determine the blocking capacity. And another thing is this region also acts as a base of the BJT. Correct? This is the base and also drain. Please know that base and drain is nothing but this N region. Okay, this is the collector region of the transistor. Okay, this is the emitter. N plus is emitter region of the transistor, and this acts as a source and drain. P region body acts as a source of the this source and drain of the MOSFET. Okay, then P region body, it interfaces is formed by region with N minus. N minus is drift region. Prevents latch up issues. That is. Just note down latch up is many things we cannot explain because it is semiconductor, all this thing beyond our control. But the function alone you should know. The region ensures the IGBT function like a controlled switch. Please note that IGBT is used. Okay. So then the last region is N plus region, which is called as emitter region. Emitter of the transistor. The highly doped N plus region allows electrons to enter into drift region. And it also forms emitter of the BJT. Please know that in case of this one, the positive charges are moving from here to here. And electrons here, they will move like this. The holes are moving like this from the collector to emitter, which is N plus, P plus to N plus. That we call whole positive charges. Meanwhile, electrons from this one equal number of. So then only current flow will happen. Correct? So when current happens, this is, you don't worry about it. That's how it works. So these are 4 layers. How it works, I explained. Okay. Now that we know how what are the important layers, there are 4 layers of the semiconductors. In the 4 layers, there are 3 junctions. J1, this is called J2, this is called J3 junction. And so 3-layer device. Functionality already we talked. Now this figure shows how to make our IGBT work. N-channel IGBT we are talking. P-channel also. Only thing voltage and the N-type material, P-type material, all this thing changes. Okay. As I told you, you need to apply external voltage. And this is my load resistor RL. RL is connected to in series with the collector is connected to positive terminal of the VCE, some book VCC. Please note that voltage between collector and emitter, or sometimes this is just VCC, which is the connector between collector. So this is the main voltage and which is going to drive. So this current flowing will be called IC, collector current. And this is my output. As I told you, this is my output. What is my input? Input is connected to gate to emitter voltage. Correct? So you can see that positive of the VGA. This is called a control voltage. Okay, control voltage of applied between gate terminal and emitter terminal. Correct? If I vary this voltage 0 to 5 volts, my IC will vary, for example, 0 to 100 amps. This is my IC. Okay. So how it works is mentioned here. As I told you, this picture is important. It will understand. As I told you, first layer is P plus, injection layer is the interface with drift layer N minus. So this is junction 1. The N minus drift region is, this is the interface. Correct. This is J2 junction. P body. Correct. P body and a drift region. And P body or P region is interface N plus the third. And another most important thing what you have to note down is, you can see that in the MOSFET, the gate voltage is not directly connected to gate terminal. In between, you have SiO2, which is an insulator. Correct? That is what metal, which is called as metal oxide. Correct? Sometimes MOSFET is metal oxide semiconductor field effect transistor. This insulator acts like a capacitor. What is a capacitor? You know that capacitor consists of two terminals, the two conducting plates separated by a dielectric media. Correct? Already we saw in the mechatronics. I have, this is my dielectric material, dielectric means non-conducting material, or insulator. Correct? Insulator, one side is, we have one plate P1, other one is P2, both are conducting plates. Please note that one side N plus is a conducting region. It is not a metal like a pure capacitor, but still it is conducting. This is a conducting region. The correct N plus the whole region conducting. Above that, I have metal contact. I am giving a battery. Correct plus. So because of that, what happens here? The voltage is induced. Correct. Electric charge. What charge? Plus charge is induced on the top side of my insulator. But now, once you apply, what happens is this positive charge on the top side attracts what I told in N, this one, you have electrons, correct? Electrons will be attracted. So this electron will come and form a layer here. Correct? So that will also enter inside the P region also. Correct? You can see that this is minus means electron. I put a green color minus. So it forms a conducting region. So the electrons are conducting. If you remove this voltage, this positive charge will not be there. Please note down. If I remove this VGE equal to 0, I applied only this voltage. For example, 1000 volts. Understand? Plus minus applied between the emitter and collector. So the IC will not flow. IC will be 0 when VG equal to 0. Now what I did, I wanted to see that current flows through my load. That means I want to make my IGBT to conduct. Then what I will do, what I did, I applied a voltage. For example, I applied 5 volt. Correct? I apply 5 volt. Once I apply, immediately a positive charges comes here one side of this insulator. Please note that this positive charge can enter because there's an insulator. Because of that, negative charges are attracted. You can see here I put negative charges, which is available inside. Right? So they form a conducting layer. So this part makes a conducting path. Correct? Conducting path is done. Let me clear, you will understand. So that means this is a conducting path created between the drift region and N plus region. This is a drift region. P was initially preventing. Now, since you apply external voltage, the poles were injected, they try to reach automatically equal to this one. So the minus part, this one, the current start flowing. Current is flowing in both this one, and they come together, right? Finally, circuit is closed. Any doubts, please? If you have doubt, please ask how it might, because if you are asked to draw the IGBT, N-channel IGBT, explain is working. So you are expected to draw this diagram and explain what we discussed yesterday and today. Any doubts? Okay, no more. Fine. So anyway, what I already explained now, I am going to complete in wordings. Correct? You can see the IGBT. How is the insulated gate MOSFET is a 4-layer semiconductor device. Gate terminal insulated from the semiconductor by layer of silicon diode. Correct? So the black color is insulated. Correct? So the gate terminal is this is my gate. In between, I have insulated. Correct? So that means, sorry, this should be like this. Extremely sorry. This should be like this. The conducting layer should touch. Okay, this is my insulator. So then the primary structure P substrate, as I told you, P substrate is called injection layer, which forms the collector. And next layer is N minus layer, which is called a drift layer. And the third layer is a P type layer, correct, which is going to form, which is connected close to N plus, which is going to be called as emitter layer. Okay. And please note that the N plus layer which forms the emitter is embedded inside the P layer. Embedded means this is a pool, correct? And which we have doped N plus. That's why we say that it is embedded. N plus layer is embedded inside the P layer. N plus layer is your emitter. Then junction 3 is formed between N plus and P region aside. Junction 2 is formed between P plus N minus layer. And then while J1, this is J1, this is the J2, this is the J3 layer, is formed between the P layer or injection layer and the drift layer, already shown here. When if I connect external power like this, as I told you, the holes will be injected from here. Holes plus charges will be pushed inside. That's called injection. That's why it's called injection. From injection layer, P plus layer, when I connect the external voltage only happen. If you don't connect the external layer, the holes here cannot enter into the system. It needs additional energy. Who is providing? The external bias voltage, which we call as VCC or VCE. That is going to push the holes inside the drift region. They go inside, finally reach here. So the current flow happens. Right? So now we'll see that the keywords are very important. When I give the external voltage between the emitter and the collector, VCC plus minus, then also you have to give the gate voltage, correct? Also you have to give positive gate voltage. Sorry, gate should be positive. This is plus, this is negative, correct? The VGS, then only conduction. Why? Only when if I don't give this voltage, this will try to go inside, but this fellow prevents, correct? Here it is blocked. Now, if I give VGS, what happened? As I told you in the previous slide, a conductance region is formed because this voltage attracts the electrons from this and they form a layer. So in this, so then this flow, they can go and combine and the current can flow. That means VGS has to be given. That's what we are talking. Holes will be injected when VGE is greater than 0 volts. Okay. When VGE, that is this voltage, this is called VGE, is equal to 0, this cannot happen. Injection is not possible. You have to apply a positive voltage here. For example, I said 1000 volts, and also apply a positive voltage VGS. For example, 2 volt, 3 volt, 4 volt, depending on how much current you want. When VGE is greater than 0, then what will happen? The injection from the injection holes will be injected. This happens. Okay. So what happened now? Once the holes enters here, what will happen? The high resistivity of this region. I said very few electrons are there. That means the conductivity of N minus or the drift region is very bad. This is a poor conductor. But once P plus holes are entering, conductivity increases. Right? Resistivity of the high resistance end drift region decreases. By holes is a charge carrier which enters means automatically resistivity reduces. We say the conductivity increases. This is called as conductivity modulation. That's how the IGBT works. How the conductivity modulation happens? By varying my gate voltage, gate to VGE. If I vary from 0 to 5 volts. For example, VGE may have 5 volts. It can be 10 volts. If I give 0, no conductivity. If I give 1, conductivity happens. Yeah, the holes are injectable. For example, 10 holes are injected. Now, if I give 2 volts, VGS, 10 holes. If I give 3 volts, 15. Like that. As I give the 10 volts or 5 or whatever maximum allowed, more number of holes will enter, conductivity increases. That's how it works. So the conducting layer is formed, as I told you, that a conducting layer is formed only when a VGS is provided. Sorry, VGS is like this, minus plus. Gate should be positive voltage. Okay. So when VGE is positive voltage, greater than 0. So it happens. So then switching of the transistor happens and the breakdown happens, current start flowing through the load. Okay. So I will close. Now, how the IGBT works? IGBT is a voltage controller. Again, I talked to many times. There's no need to talk. But that means basically a small change in VGS. For example, the IGBT, the gate to emitter voltage, control voltage. If you see the data sheet, they say 0 to 3 volts, 0 to 5 volts, 0 to 10 volts. This will be the voltage, not 0 to 100, 200. Okay. But this is my VGE, control voltage. If I vary a small voltage, 0 to 1 volt, immediately the collector current flowing from the collector to emitter through load will start increasing, correct? From 0 to 100 amps, 0 to 500 amps, depending upon rating, right? So that's how it works. And IGBT operation can be represented 3 states. One is called off state. Off state means when the gate voltage, correct? VGE or VG. In this case, it should be VGE. Sorry, correct? VG is 0. IGBT is said to be non-conducting. Even though we supply VCC. VCC is supplied emitter to collector, for example, 1000 volts. But my VG is 0. That is off state, correct? My VG equals 0 means the IGBT will not work. If I want to switch on my this one, my VG should be greater than 0 volts. For example, I say VG equal to 5 volts. What will happen? Automatically a positive gate voltage. And again, one more thing, but to MOSFET to conduct, you need to supply a minimum voltage, minimum VGE, a minimum VGE, which is called a V threshold. If you see the IGBT specification, they say threshold VTH, threshold voltage. That means, for example, my VGE was 0, correct? Automatically, my IC is 0 because VG is 0. Now, I increase VG equal to, for example, 0.5 volts, correct? Immediately, I said the IGBT will start conducting when VG is positive, greater than 0. 0.5 is a positive voltage, correct? But still, you will see IC equal to 0 only, correct? That means now I increase my VGE, gate voltage equal to 1 volt. Immediately, I see IC equal to 10 amps current is flowing or 5 amps current is flowing, correct? So you may be wondering what happened here. That means this MOSFET, which is the input of the IGBT, has a threshold voltage of, for example, 0.9 volts. They say V threshold equal to 0.9 volts. As long as my input voltage VG is lesser than 0.9, we know that in transistor, what we talk, base voltage VBE, VBB is less than 0.7, my transistor will not conduct. IB will not flow, IC will not flow. When 0 to 0.69 volts, my transistor will not conduct. If I increase the base voltage to 0.7, immediately start conducting. 1 volt, 2 volt, up to 5 volts. Correct? VB max, 5 volts. 0.7 and greater. Similar to this, MOSFET also, they give what you call the V threshold. Sometimes some book put VT, some book put VTH of the MOSFET. Correct? What it is? Threshold voltage. That means if the threshold voltage of the MOSFET is 0.9, if I vary the VGE of my IGBT 0 to 0.9, IC will be 0 only. Collector current will not flow. My load will not work. my IGBT will not conduct. If you want to make it, what you have to do? You have to give VG is greater than VTH. That's what I mentioned. Then only this one. Generally, we want VT should be smaller. Smaller is better. VT equal to 0.1 volt. 0.2 is much better MOSFET or better IGBT. That you have to note down. But there are many issues are there. Now, during onset is happened. Then last state called saturation state. In this state, IGBT enters into fully conducting mode. We know that transistor also, I saw IB can vary from 0 to 10 milliamps. And this is my IC, vary from 0 to 100 milliamps. Correct? This is my emitter, collector, base. What is my IB? We know that. That means if IB is vary from 0 to 10 milliamps, my IC will vary 0 to 100 milliamps. If I give 1 milliamp, IC will be 10 milliamps. If I IB equal to 2 milliamps, the IC will be 20 milliamps. Correct? My beta equal to 10. That's what it is. You understand? Okay. Now, I told you, if I give IB equal to 10 milliamps, correct? Which is called as such IB max. Correct? We call it. Then IC will be 100 milliamps. IC will be 100 milliamps. If you see the data, if I increase IB to 11 milliamps, still you will see that IC will be 100 milliamps only. I make IB equal to 12 milliamps, 15 milliamps, still my IC will be 100 milliamps. So I say that my transistor is saturated. That means the maximum current can apply to base is only 10 milliamps. And because of that, there will be 100 milliamps current will flow. That IB of 10 milliamps and IC of 100 milliamps are called saturation currents. Similar to that, since my IGBT output stage is a transistor, correct? If I give a maximum voltage of, correct? For example, VG equal to 10 volts. That's what there's a VG max of the IGBT. Then what will happen? My IC max may be 100 amps. During that time, if I measure VCE across the emitter and collector terminal of my IGBT, correct? Across this, if I connect a multimeter, that will be VCE set will be equal to 0.2 volts. Why? Because this is a transistor. In silicon transistor, when transistor enters the saturation, that means in the base, you applied a maximum base current. Because of the maximum collector current is going, automatically the voltage drop across my transistor collector emitter VCE sat will become 0.2. Then that are advantages. That is one of the most important advantage of using transistor at the output stage of the IGBT. Because of the very low saturation voltage 0.2, and even if very high current flows between ICE, correct? The VCE multiplied by IC max is nothing but power dissipated across a transistor. This will be very small. Yesterday I told you the power dissipated across the IGBT transistor MOSFET should be 0. All power should be dissipated across low distance. But between the collector and emitter, or between drain and source of MOSFET, or between the collector and emitter of the power transistor, or between the collector and emitter of the IGBT, there's a voltage drop. In case of transistor, VC is 0.2. But in case of MOSFET, VDS, that means voltage across drain and source will not be 0.2. Generally, it will be higher, 0.5 volts, 0.1 volt, something like that. So that means more power will be wasted across the MOSFET. That's why the IGBT combines MOSFET as input stage, transistor output stage, so that the power losses can be reduced and it can work. Okay. So already we talked about this voltage rate, all these things. I'm not going to discuss. 3 stage we have talked. And this one talks about what you call input output character IGBT. Correct? Input stage, you can VT is nothing but MOSFET threshold voltage. Okay, I told you this is my VGE. When VGE equal to 0 volts, MOSFET will not conduct. Correct? So my transistor will not work. Output stage. So you can see that up to threshold range, I am increasing the VGE. For example, I say that this is the 5 volts. Maximum voltage, you can supply 5 volts only, they say, right? So I increase 0, 0.1, 0.2 like this. For this MOSFET, say for example, 0.9 volts is the threshold. So 0 to threshold, you can see the current doesn't exist. Y is the IC, output current. Input is the voltage of the MOSFET, gate voltage. Output is a collector current, which is going this one. As I increase voltage, you see the current is not in. Once I cross the threshold voltage, which is 0.9, you can see that immediately current start increasing. This is called a input-output characteristics of the MOSFET. Okay, but this is input stage, MOSFET. MOSFET is driving the output of the MOSFET, correct? What is the output of the MOSFET? You can see here, the drain current, ID, that is controlled by gate voltage. If I vary the gate voltage VGS, the ID will vary, which is nothing but IB, correct? IB is nothing but base current of the output stage. So IB equal to ID. If VGE is changed, varied 0 to 5 volts, my ID will vary from 0 to 10 milliamps or 100 milliamps. This is given as the base to the power. So my beta equal to 1000, correct? Then, for example, 1000, what will happen? If I vary the base voltage, that is gate voltage from 0 to 5 volts, my ID varies from 0 to 100 milliamps. So that will be multiplied by 1000. So 100 amps current will flow. IC. That's how it works. You understood? Okay, fine. So this is called collector output state. Input to output to VCE. I told you this can be 1000 volts or 400 volts, 600 volts, maximum voltage, because output state. And this is a collector current, correct? And VGE, if I vary the VGE for different VGE level, you can see that collector current varies like this. When I vary the VCE vary from 0 to 1000 volts, for example, for given VG equal to, for example, plus 1 volt, right? If I vary this 0 to 1000, my current will go like this. Instead of that, my VGE, base voltage, is given equal to plus 2 volts. I'm keeping constant. Then I'm varying VCE 0 to 1000 volts. Automatically, my current will vary like this, right? So we can see that all the current increases, and such. This is called as saturation. This line is called as saturation region. Beyond that, I cannot apply voltage. This is equal to 1000 volts, which is also called a breakdown voltage. For IGBT, maximum voltage, they say VC or VCE max of the IGBT, for example, 1000 volts means that is the maximum voltage you can apply, which is also called as breakdown voltage, avalanche break. Beyond that, you should not give. If I give 1500 volts, my IGBT will fail. Heavy current will flow, it will destroy. So this is input-output characteristic. The output transistor, this is input MOSFET. Input-output characteristic, both are connected together. Okay. So again, I told you, just take a few minutes. I want to close this today. You can see that IGBT, we talked about transistor, MOSFETs, and IGBT. Please see that compared to transistor, MOSFETs are better. MOSFET can work because x-axis is the frequency operation, 0 hertz to 1000 kilohertz, the axis. But generally, most of the power transistor will up to 100 kilohertz only. Most of the power transistor switching frequency, whether MOSFET, IGBT transistor, will be 0 to 100 kilohertz, especially power transistors. Not about low frequency, because where high currents, high voltage operated, you cannot switch it. Then it will destroy your this one. So the motors, correct? So we are talked about the BLDC motor or the permanent magnet synchronous motor or induction motor used in electric vehicle. The operating frequency will be order of kilohertz only. Now it will be always lesser than 100 kilohertz generally. This is how the MOSFETs are designed for operation. So you can see that IGBT can work at lower frequency only, can go up to 20 kilohertz or 30. Very rarely they go up to 50 kilohertz. Correct? This is this one. But MOSFET can work up to frequency also. Okay. So we can see the IGBT works on lower frequency, MOSFET works on higher frequency, but IGBT can work on higher voltage. Right? You can say 1000, 1500, up to 6000. MOSFET can work only up to 200, 400 volts. MOSFET can work only 200, 300 power MOSFETs. Very rarely you see 400 volts, not beyond that. But IGBT x-axis, y-axis, you can see that they can go up to 1000, 2000, volts also. That's what we are talking here. The key points are mentioned here. Power MOSFETs are advanced higher commutation speed and greater efficiency at low voltages. That's why we said up to 200, 300 volts. It can operate high blocking voltage, maintain high current MOSFET, but since again it is under low frequency range only. But if I want to operate higher frequency, correct, then I have to go to IGBT. IGBT is a higher current density because output is a transistor. Power transistor, note down. Power transistor can conduct high current compared to power MOSFET. So that's why output stage in IGBT, you are using power transistor. High current is possible. Low power, VC is actually equal to 0.2. So the power dissipated is less. But I want higher frequency operation that is taken care by MOSFETs. So combining this, we can get this. Key point, another important point, what I just wanted to talk is IGBT has higher current density at output stage because I have transistor. Okay. Single IGBT can replace 3 or 4 or 5 MOSFET, power MOSFET. For example, I want to drive, for example, I have electric vehicle, I have lithium ion battery, which is a 500 volts, correct? And I have a motor, for example, 100 kilowatt motor, correct? Electric vehicle, 100 kilowatt. P equal to VI. And I say 100 into 1000 watts equal to V equal to 500, and I can find out I equal to, you know that 1 lakh divided by 500. Right? 2 zeros are gone. This is gone. 5. So that means this much current is going to flow. 200 amps current is going to flow. Correct? I will go to 200 amps current will go inside. Yeah, there's one more zero I missed. 200 amps current will flow. Okay. So for this power MOSFETs, generally you need to put the most of the time 50 amps. Is in most of the time very rarely 100 amps. So if it is 200 amps, if it is 50 amp power MOSFET, you need 4 power MOSFETs. But IGBT, I already told you, they are available up to 1000 amps, 1500 amps. So single IGBT can replace 4 or 5 MOSFET to drive 600, 500 volts, 100 amp, 200 amps motor. So that means my controller will be compact, only single power. There is a compact, and so the advantage of IGBT. Okay, last slide. Please take this. As I told you, comparison between the IGBT power transistor. We are all talking power. Voltage rating of the power transistor will be less than 1000 volts, 1 kV. Correct? It is high, but lesser than 1000 volts. But in case of power MOSFET, also same. Power MOSFET, power to individual. But in case of IGBT, they can go up to 6000 volts also. I told you yesterday. Correct? Greater than. So the IGBT can operate much higher voltage compared to BJT transistor and MOSFET. Second one is current rating. Most of the power transistors can go up less than 500 amps. Correct? Less than 500. 500, 400, 300 is not less, but even though very high, but you can see that this one can go much higher. IGBT can go higher than this one. So the input voltage, this one, current ratio, the call is 200 to 20 to 200 in case of the power transistor. But in case of power MOSFET, we say here, please note that what is input for transistor IB, what is output IC. IC divided by IB is sometimes called HFE ratio. Correct? In case of transistor, it will be 20 to 200 most of the time. Correct? Power MOSFETs we are talking. Okay. But in case of power BJT, in case of power MOSFET, the control voltage is generally 0 to 10 volts. Okay, which is going to control the current flowing up up to 500 amps. In case of IGBT, it is almost same because same power MOSFET we are using input stage. The input impedance of transistor is always very low. Correct? We say Z-in, we saw. But in case of MOSFET, Z-in is very, very high. We talk about this is in the order of kilo ohms, this will be in the order of meg ohms. Correct? So MOSFET has advantage compared to this one. That's why in IGBT, we are using MOSFET as input. So Zin will be in the order of meg ohms, 1 meg ohm, something like that. Output impedance of transistor is low. Correct? Power MOSFET is, sorry, this is not, it is not very low. It is slightly high. Slightly high. Sorry, well, typo mistake. Compared to power transistor, output the resistance between collector emitter with this one, this is drain between the slightly high compared to the. But in IGBT, we are using same transistor. It has low output impedance. Due to this, the power dissipated, power wasted will be low. If output impedance is low, the power dissipated by the device will be less. So that means IGBT will have low losses, transistor will have low, but MOSFET will have this one. Then, but when you compare to switching speed, correct? Switching speed, you can see that power transistor slow. Power MOSFET, we are talking switching speed means in terms of switching time. Switching time is in microseconds. But in case of power MOSFET, it is nanoseconds, 10 power minus 9, correct? It is better. But in case of IGBT, it will be medium. Okay, it is not very fast like MOSFET, or not very slow like a transistor, it is medium, right? In the order of microseconds and frequency 25 kilo or something. But in case of MOSFET, it is 100 kilohertz, here will be less. Finally, the cost. If I buy any device, if you do build a device, you will always see the cost. Cost-wise, power transistor low, but MOSFETs are slightly medium, but IGBT are expensive. But please see that even though it is expensive, single IGBT can replace 3 to 4 power MOSFET. Then overall cost can be reduced. Okay. I talked all those things. I'm not going to talk. Finally, this is the last slide. Please see that I want to drive the electric vehicle motor. This is an electric vehicle motor. This is my lithium ion voltage or 600 volts or 500. This is my IGBT. Correct? IGBT. This is my collector. This is my emitter. Correct? This is my gate because it is IGBT and it is getting signal from my embedded controller, vehicle controller. It generates a PWM signal, control signal, supplied to opto isolator, so that here you have 600 volts. Correct? This voltage, something happens, should not come and kill my vehicle controller. Then big issue. That's why many times, whenever you want interface a high voltage circuit, this is high voltage circuit. This is called low voltage. The microprocessor works embedded controller with 5 volts and few milliamps. Correct? Few milliamps. And here 1000 volts and say 500 amps or 200 amps. Correct? Very high voltage. And this one. So if something happens in this one, this voltage should not come and destroy my embedded controller. So what they do is the control signal from my embedded control, PWM control, this is my control signal, will be given to what is called opto isolator. From opto isolator, output is given to control this. Okay. So this is what this one. The last slide, applications are enormous. Industrial application, wherever high voltage, any application which require high voltage, high current will be using IGBT. I stop here. Sorry for taking another 15 minutes or 20 minutes more. I want to close this. With this, our power electronics is over. And tomorrow, we'll have 2-hour teaching, 5 to 7. I'm going to talk about energy storage devices. Okay. After completing energy storage, it may take 2 to 3 hours. Tomorrow, 2 hours. Maybe next week, another 1 or 2 hours. After that, I will talk about MOSFETs, which I missed. Right? I think I missed MOSFET. I will teach one class after energy storage device. Then last chapter will be talking about the computation of the torque requirement, power requirement, engine sizing, all those things. That will be another 5 to 6 hours or 7 hours will take. With this, we'll close. Any doubts, please ask.
Sir, only thing we have another some 4 or 5 classes also. So up to April 15th, after April 30th, we have the classes.
When did we say the exam?
9th and 11th, sir. 11th.
11th. No, 11th we have. So I need another 8 classes minimum. Before that I cannot complete. 8 to 9 classes are needed.
And then we can have it next week, Thursday also, sir.
Yeah, we will have next week also. From Apart from today, I need 8 to 9 classes minimum to complete the portion.
It's the sixth class, and tomorrow we are going to conduct.
Okay, sir. Okay, sir.
I will complete before 30th.
Right, sir. Thank you.
Correct. Whatever other teachers, they have completed.
Completed, sir.
Sir, Shakaram completed a project. He has given 2 projects, sir. That project is right now is going.
No.
Theory class completed, sir.
Sir, Shankaram sir has completed, sir.
Okay, what about Anand? Hello, Anand? 2024 batch, no?
Chidambaram.
So not yet completed, sir. We are in module 2.
Okay.
I mean pollution. He finished ice engines. He's now teaching pollution.
Okay. Oh, okay. But don't worry. We will stick to our this one 6 to 7. And every Thursday we'll have 2 hours.
Okay.
Correct? So
Even next week, Friday and Saturday also we can take, sir.
yeah, I want to complete before 30. I need the 8 to 9 classes. I will complete.
Okay. Thank you.
Before 30, I will complete so that you can prepare well and can write your
That
exams.
is what, sir. That is the main.
I know that. But that only thing is I will ask additional classes. Maybe even Saturday I can take or Friday I can take 2 or something.
Yeah. We will be ready, sir.
Okay. Very good. Nice. Thank you very much. See you tomorrow. Have a good night.
Good night, sir.
Please.
Good night, sir.
Good night, sir.
Yeah, please give your attendance before leaving.